like an internet problem. I hope everything okay. So if you have problem, just tell me via WeChat. I think WeChat is better communication instead of chat in the Tencent. I think it's better like for people notice it. I mean Tencent side. I hope you guys can listen my voice. And then okay, and then lecture note is more or less finished reading for first semester. Okay, seems okay. And where we were? So we are talking about, oh yeah, we're talking about Shalem. Shalem. Spectral representation. Oh, I forgot to bring the homework, graded homework. But anyway. Okay. It's quite amazing. Students still come to my lecture to classroom. That's a good sign. He wants to learn. And still, even Tencent side, there are many students. Oh, amazing, 23 students. And many people come. Amazing. Okay, so let's get started. So last time we at the end of like a 20 or 30 minutes, we start talking about the Shalem-Lemon spectral representation. So recall that this guy's name is pronounced as Shalem. He's Swedish. Maybe more precisely, there's a double dot here, and then this way. And I met, as I mentioned, his grandson, and who used to be a string theorist. Anyway, yeah. So we talk about the interaction theory, how the operator create the state. So interaction theory, the operator phi. So we are talking about the example of scalar operator. Not only one particle states, so it also creates the bound state and the multi-particle state. So therefore, Hilbert space, if you sum of all the Hilbert space, omega is vacuum, and the sum of lambda and QT 2 pi Q over 2 EP is the Lorentz invariant measure and lambda P. That's the identity operator. So this is the vacuum, of course, vacuum. And these are any state, excited state. It's with momentum P. That's what we can. So lambda P can include one particle, multi-particle, multi-particle and bound state, any state. Sorry about I cannot turn on the light. If I turn on light, the Tencent side cannot see the blackboard. So yeah, anyway, hopefully it's okay for you guys. And what we try to do is that we try to see how the propagator look like in the propagator is in interaction theory, because we skip lots of detail in the interaction theory. So we just omit the detail of the propagator in the middle, and we come back to the point. And so here we just insert one inside a middle. So then this can be written as of course, the omega phi of x, omega, and then omega phi of y, omega, and plus. And then you just insert here. So lambda dq 2 pi q 1 over 2 dp. And then omega 5x of lambda e and lambda e 5y and then omega. So that's what we have. And as we go, so unfortunately, yellow is better or red is better. I don't know. So this is 0 because so if you recall, phi of E is indeed equal to Z because it's invariant. So the vacuum is the vacuum in here and the vacuum in here is a translation invariant. So therefore, which means that more precisely, e to the I p x is equal to So therefore, p acts on omega should be 0. So therefore, it becomes identity operator. So therefore, and recall that the phi of x is e to the ipx phi of 0 and e to the minus ipx. I'm very sorry there's not so much space. And then plug that into here. So this is equal to phi of 0 omega. Omega is sandwiched by phi of 0. And this is, as you can see, constant, just constant. And the constant, so phi can be shifted by this constant. So therefore, you can freely set this one is equal to 0. Therefore, you can ignore. So can set to be 0. Set to be 0. That's what we explained, and this is goal. And then now we focus on this guy. And this one is also can be manipulated a little bit more. For instance, phi of so omega phi of x, the p is equal to again omega. So last time I just rushed through it here, so let's just recall a little bit. Minus I x lambda zero. Zero is the momentum. So lambda p. So okay, and then here this is phi of x, phi of zero. So p axon omega is zero, so therefore this is identity operator. And then p axon this one, this is p is actually the operator in quantum mechanical sense. Operator momentum axon this guy is just like give you the scalar quantity e to the minus pi x. So this is now it's just the product of just for momentum. Here we treat p as an operator. P axon lambda p, we get the p. Just that's what I mean. So therefore, you can just push out of this product, and then applying the Lorentz boost, boost. So as you know, I mean here whatever E and P, whatever, and there is a light cone. Oh my goodness. That's showing the line, unfortunately. Light cone, and you have E square minus P square is equal to M square. And so now lambda P, oh, where is it? Lambda P is something like this one. The P is whatever. P is momentum like this one. If this is the case, if you do the Lorentz boost and bring this vertical line to the like this line. Anyway, you already know. We already used lots of techniques like this. So we. Unfortunately, you cannot distinguish. Okay, let's use orange maybe. Anyway, so the boost is this is spatial and this is time. So this is Lorentz boost. From here to here is I call it U. This is the Lorentz boost U. And then so then what we have is the so this is equal to omega U inverse U phi 0 U inverse U lambda P E K minus I P X. And U axon lambda P is indeed U Lorentz boost does not change the vacuum, of course. So therefore U phi of 0 U inverse lambda V. That's what. And then, as you can easily see, so this is the Lorentz boost acting on the phi of 0. And then the position of 0 does not change. Okay, even if you do the Lorentz boost, the 0 is 0. So therefore, this is equal to omega phi of 0, lambda 0. Okay, so this is a manipulation one to do for this guy, for this guy, for this guy, and then we can do the same thing for this guy. Okay. So at the end of the day, so what we have is this correction function. To phi of 0 e to the minus IP x minus 1. That's what we have. And then we stop this one at this at the end of the lecture. So okay, and then we can just rewrite in Lorentz invariance manner. So we can just rewrite this one is already we know many times. this guy can be written in the form of momentum, like what we have done in propagator. Square and lambda square plus epsilon. This is what we have already done for propagator. And then e to the minus 1 t x minus y. Then square. So this is exactly the same. Exactly the same. Okay, so that's, and we call this one is the df. It's the same as final propagator. Maybe I call it m lambda square. I call it m lambda square. And then we can just rewrite this one as the following: 0 infinity d m square rho m square, and then df x times y. Oops. Okay. Like this one. Yes, go ahead.
Why should of this term to be similar to anything other form?
So can we take other? I mean here, so what we use the Lorentz invariant phase space. So this is, as you know, so Lorentz invariant phase space. Phase space. And then this can be written, this can be manipulated in, as you already knew, to this one, the propagator. So that's the origin of the propagator. And then, so what's nice? Yeah, what's nice is that the otherwise this identity cannot be written in Lorentz invariant manner. So if we don't use Lorentz. And then furthermore, what's nice is that the if you plug that one into two-point function in here, the important thing is manipulating here. What you get is this scalar quantity, scalar, like some. It depends on yeah, it's independent of p. So therefore, this one can be bring out of the momentum integral. Because this is the already if you do the momentum shift and the Lorentz boost, this is already p is gone, right? P can be set 0, right? P can be set 0. So therefore, you can just bring out of them this momentum integral. Therefore, propagator can be treated independently. So that's a very nice thing. So then, so if you bring out of the momentum integral, the cost is this rho of m square, and then rho of m square can be defined as the rho of m square sum of lambda m square minus m lambda times sorry. Zero, then lambda 0, and this. So if you plug rho of m square into here, so delta function just plug m lambda into here, and then what's left is this. Okay. And then let's examine what it means from now. It means from now, let's see. I brought to eraser. Okay, and then so phi of x will create this kind of stuff. Okay, this kind of, and then rho this, and as I mentioned, so this is called spectral density function. Density function. And then, so this rho m square takes the following form. M square. So one particle stays at the, of course, the around m square, and there's a delta function here. And the multi-particle state starts from 2m square or 2m square around here. I hope you can see, and everything become continuous. Continuous. So here is the capital M square is this m lambda square is the center of the mass, and then of course if you have a two particle states, and then they can whatever move into the anyway, but if you go to the center of mass, if the momentum is opposite, p and minus p, and if it's two particle and then the center of mass does not move, but p can be freely changed, right? P can be freely changed. So therefore, the spectrum becomes continuous for multiple particle states. So that's and as you recall, bound state is something like a if you have a potential interaction theory, one can put the potential, and then so as you recall, if you have a potential something like this one, and this is x potential here, one can just have the bound state is something like this one. A bound state is sitting like here. Bound state sits like wave function takes the point from. Sorry, my drawing horrible like this way. In any case, so what I meant is that due to potential, it's trapped into the less than zero, right? So therefore, less than the original the two particle, the mass of sum of the mass of two particle states, which means that it's a less than 2m squared for bound states. If you trap inside below the potential below the zero. So therefore, so it should be that the total energy is less than the sum of the two particles. So these are one particle. Okay, so number one, number two, number three. This is number one, and these are number two, and this is number three. So this is a typical form of the spectrum of the states. Spectrum of states in interaction theory. Any question at this? And then yeah, so the total energy of a multi-particle states, I mean, depending on momentum, it can be continuous variable. And then moreover, if you look at this is 2-point function, or propagator. The propagator has the This is the P0. And then I think the CF P square. And then usually it takes a form of for single particle states, the propagator is like this, df of the momentum space. So therefore it has a I think I need to go to this Peskin. I didn't. Sorry. I think I didn't write down in the lecture note for this figure. I think is it P square? Maybe I should go to the Peskin and oh yeah, I think P square. Sorry, this is P square state. P square. You just treat it as a P square. There is a pole at the M square for one particle states, and there's another pole at the left. Okay, and there is some branch cut starting from 2m square, and there's a branch cut means there's a branch cut. Due to the this continuum of multi-particle states. So therefore, here you always have the some part phi x, phi or y can create some multi-particle states which has a pole at the m lambda, pole around here. So therefore, which create a so-called branch cut. And then, of course, you have some additional a pole coming from the bound states. So that's a typical 2-point function in interaction theory in momentum space. That's what's. So therefore, maybe I should write that this is number 1, and these are, sorry, oh my goodness, number 2 and number 3 coming from. So that's a typical the 2-point correlation function in momentum space in interaction theory.
How can we see that it's a branch? Oh,
because it's continuous. So therefore, here you always have some pole or like if you set the p square in these values, you get the infinity. That's what the branch cut means. Always. And then usually when you write down the propagator, whatever scalar propagator, which is usually this is the propagator. I mean, it's depending on complex scalar or here real scalar. So I'm not going to write down the direction and the p. So we only p. Usually, when you write down like this way, we only pick this guy. We only pick this guy for in interaction theory. This guy. So this propagator is really only one particle states. We just take this.
what does this act on? In some non-fluid series. A clear definition.
If I mean, here we talk about the weak coupling region, so that you can just do the perturbative expansion, and then you can just write down the we can just write down. I mean, we can calculate. We can apply this Feynman diagram, loop diagram, and just calculate. That's so. Here we assume the weak couple region.
So what's the relation here?
Yeah, this is literally m lambda. This is it. I mean here is the delta function, right? M lambda. So this pole m lambda here, there's a pole. Pole here is literally the pole coming from the state lambda. So it's just this delta function just replace capital M square by small m lambda. That's what. Any other question? So this is called the Shalin-Lemon spectral representation. More precise, and then usually, so we just how to say, distinguish this one particle state to the others to do the perturbation theory, So what we have to do, in the following way. To distinguish the one particle from the others, so we just write down we are going to do the momentum space, the force e to the r times p x times y, and omega phi of x, phi of y, omega, and this is equal to I c over p squared minus m squared plus I epsilon plus m bound dm squared, and rho I call it prime, I prime and squared, I over squared minus m squared. So rho prime m squared means that we just get rid of one particle. We just distinguish one particle state from in this spectral density function, which means that we just rho m squared. We just write down like this, right? Delta delta m squared minus m squared. This is one particle state with the omega phi of 0, and then this is one particle states. This one means one particle, and plus rho prime. So that's, I have written this. This one means one particle, and and we call this one is equal to z. Yeah, z. And then this 2-point function in momentum space take the usual one particle propagator plus some other bound states or particle states. This is a typical form, and this z can be understood as the field strength renormalization. Okay, so this z appeared in the previous calculation in the right. In previous calculation, so the z appear. So if you just do the strength normalization, is equal to usual p, what p plus we already did many times I plus I and dot 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 dot. And if you incorporate all the quantum correction, which is something like whatever you already know. So this includes something like this kind of diagram in FIFO theory, for instance. Include FIFO theory and do that. You have to do the loop evaluation by using whatever we already did in the. You guys already did the homework, right? Find one parameter weak rotation, dimensional regulation, or power Wheeler, and what you get is this is equal to IC p squared plus m star plus IB. And this is the we call this one is the field strength renormalization. Strength normalization or wave function I mean it's the same function. And this m, the position of m is the elements. M0 squared. So that's what we have learned by evaluating loop integral. But this Z natural should appear just appear between the transition amplitude from vacuum to one particle states, which is created by this operator phi of Z. So therefore, the total amplitude should be so. Yeah. Anyway, so this. So this is called the Shalin-Lemma spectral representation of the two-point function. And then since as you can easily see, you have to, the phi can create these kind of like a different states, which means that the one particle state, this not only create one particle state, the other states. So that which means that the Z has to be less than 1. Because the probability, in total probability should be equal to 1, which means that the probability that create the operator create the one particle state should be less than 1. Therefore, Z should be less than 1. So therefore, here field strength renormalization should be less than 1. And then we can apply the same thing for other field. So here we only talk about the scalar theory, but you can also do the same trick. You can do the same thing in the I mean, you guys already familiar with it. So this is time order. Sorry, time order. Did I write time order here? Sorry, I missed time order. So you should put time order here. Sorry. And yeah. Sorry. So phi, psi bar, omega is again same thing. IC2 is slash minus m plus I epsilon plus the other guy infinity m bound in interaction theory impermeable dm square rho prime m square I times p slash m plus I. Hopefully you can see. So this is the form of the spectral representation, Shalin-Lemma spectral representation of parameter. So I hope Tencent side can read what I have written in the blackboard. Okay, so that's what's happening in the interaction theory. And then when you do the calculation of the perturbation theory, we essentially pick this part and then just roll it. And then the meaning of the wave function renormalization Z is amplitude of operator phi, which is sandwiched by vacuum and one particle state. So that's the meaning of the another way of looking at the wave function renormalization. Good. Any question at this moment? If not, I'm going to the LSC reduction formula. So again, so here we kind of omit subtlety to do the asymmetric calculation. So we just revisited S-metrics and then see some subtlety we missed in previous argument. I mean, usually in this LSD, sometimes LSD appear at the beginning of interacting theory. Some teacher or some book, whatever, teach LSD at the beginning of S-metrics. I just followed the order of Peskin. So Peskin talk about the LSD in section 7. So, and I just wanted to follow the lemon. Again, lemon. Semantic. Semantic. And then Zimmerman. Reduction. So this talk about the some subtlety talk or subtlety comes from quantum correction. To the S-metrics. So this reduction formula is essentially they talk about the S-metrics, quantum correction S-metrics. That's why Peskin and Schroeder treat in section 7. Okay, so when we talk about S-metrics, I don't know, like almost in the middle of the semester. This is the last lecture, but the middle of semester I talk about S-metrics. And then S-metrics is the element unitary transformation from initial states to the final state. And we assume when we compute the S-metrics, essentially what we have is that the initial state is a free particle. The time goes to minus infinity. The past infinity. The state is the free particle, asymptotically free particle, and then the final state is also some wave function, prime wave function, which is f. Future infinity is f and I are the free particle we assume. So these are like a free state, the state in free particle. They do not interact each other. That's what we assume in the in interaction theory, we have to be careful that the phi of x can create any like a one particle bound state, multiple particle states. So we have to be careful about how you define the free particle states in the past infinity and the future infinity. So you have to be a bit careful about how you treat I and F and operator phi to define the S-metrics. That's what this LSC reduction formula arises. And I think this is where I think I can erase here. Okay. Maybe here is okay. I mean, when t goes to minus infinity, when you consider alpha of phi of x and there, so when you consider the Bayer, so this you can just write down. So phi initial. So here, so future infinity and past infinity. So the field can be treated as the free state. So therefore, phi out of x and phi in, I call it phi of in x, where this is equal to limit of phi. Unfortunately, I don't have a space to write that. Sorry. Phi in of x is limit t goes to minus infinity phi of x. So therefore, similarly, phi out x is the limit t goes to infinity phi of x. Phi out and phi in can be treated as the free theory, operating free theory. Therefore, it admits a model expansion. So that's what we assume in the S-matrix theory. So past infinity and future infinity, the operator behave like a free field. So therefore, if you consider in the past infinity, so then this can be treated as a square root z alpha phi in of x of base. And this square z is really wave function field strength renormalization that can be just determined by this of one particle is square root z omega of phi in of whatever. Maybe 0. 0 is also okay. 0 and later. Like this. So you just rescale phi by square root z so that the propagator just takes the one here. Propagator takes the for one particle steps. That's what we have rescale the operator at the past infinity. And then I'm going to erase this part. Okay. I don't think I have time to talk about the optical theorem today. So let's talk about the LSC today. Now, play the one-box video. Even though I have written the lecture note for optical theorem. Okay. Anyway, so therefore, so we assume that the past infinity and the future infinity particle just separate. Okay, particles separate each other so that they do not interact. So therefore, phi of in and phi of out can be treated operator in the free theory, which admits a model expansion, as we learned in the beginning of the semester. Square root 2EP and in of P e to the minus IPX plus a dagger in of P e to the IPX. This in means in states or in initial states, or whatever, not interacting. Sorry. So be careful. This is not interacting. So in means initial or whatever, in state. And out like this. Out of P to the I. Okay, so that's so they admit the free field expansion. And they're related by, so as you recall, S is just time translation from, I would say T minus T. Limit S is equal to limit T goes to infinity. Okay, that's what we have done. So it's just time translation for S. Okay, so this is S. S is the time translation of the total system from past infinity to the future infinity. So this minus T is capital T is a past infinity, and capital T is a future infinity. And the S matrix is just time translation in total system. H is a full Hamiltonian. H is a full Hamiltonian in the system. And so now for the phi out, it's just S phi in. Which one is which one? Okay, sorry. Okay, this is correct. So that's what's going to. Lecture note is the opposite. Okay. So to define the initial states, we need to create. So now for initial states. Okay, let's. Okay, this is the last lecture. So initial state. Let's be a bit relaxed. Q1 Q. I call it Q. How many? I think I just wrote down the how many states I defined the initial and final. I think N R. Oh, I use R. Oops, R. QR in. I just write that. So this is essentially you have a vacuum at the infinity, future infinity, 0, and you just apply a Q1 dagger and in. A dagger in Q2 and then yeah, it's quite impressive that this is how the initial state is defined. So this the in state creates the acts on vacuum, passing infinity. And the final state is the same way. The final state is the same. Final state, I call it P1. I call it P1. Right? As far as I call it P1. So PM out. And this is the A out with P1. A dagger and A out. PM. And its matrix is just I F. It's just a transition amplitude between P1 dot Pn out and then Q1 dot QR in. And then we want to evaluate this transition amplitude for in state to final state, all states. Okay, so that's what we want to evaluate. Okay, everybody's very diligent to taking note. I'm glad to see that students still try to catch up, even though my course is difficult. Okay, so to see that this transition amplitude, first, how to define this A in and A out state, or A in dagger and A out dagger states. So A in dagger state is essentially we already did in the at the beginning of I think you guys already did in the let's see, in the long time ago in the free theory. Okay, let's recall that what we have done. So a dagger is essentially what we need to do is the inverse Fourier transformation from here, the QX, and then skirt EP, sorry, D4. E2 phi of X in and minus a plus, so minus I square root to EP and the pi of X. So this inverse Fourier transformation, e to the I p. That's what we have learned in previously. And this can be, oh, sorry. So this is Q, sorry, Q. The spatial interval. EQ. This is also in state. And then, sorry, so if you want to specify this is Q1, I call it Q1. And this should be Q1, sorry. Q1. So this is the what we have learned. So you just need the inverse Fourier transformation from here. Inverse Fourier transformation. This can be written concise manner. This can be written minus I square root to P. The cube. Call it. Ooh. I call it x1, and I call it x1. Sorry. The x1, and then oh yeah, you're right. This is the bonus like missing. Sorry. E to the minus I q1 of x1, and then partial 0. So this is time derivative, and I create this symbol and phi x. That's and where this symbol is phi mu. This symbol is defined as f phi mu g acts on here minus phi mu f. So this is a symbol I created. So this is the definition of this symbol. So if phi 0 acts on, sorry, not phi 0. Del 0 acts on phi, you get a pi, right? You get a pi. Okay, that's the definition of in free theory. Time derivative of phi is a momentum pi. And if this one acts on Q, that create the E of P, that create this upper EP. That's what it means. Okay, is it okay? Do you understand? I hope it's okay. So this acts on Q, that. No, you guys should tell me this should be Q1, right? Q1, sorry.
Yes.
Oh my goodness, I made a lot of mistake. Q1. So I will correct the lecture note later. So I have a mistake in here. I have written anyway, P here. Anyway, so the Q1, everything Q1, sorry. Q1. So this, if this acts on phi, it creates a pi. The 0 acts on this e to the momentum x, this will create the upper EQ1. Okay, so that's how you create. And then just plug that into this amplitude, and we will see what's going to happen. We're going to see what's going to happen. Okay, I think let's give up optical theorem today. I think, well, how many of you guys want me to rush a little bit and want to talk about the optical theorem today? No, right? I think no. Okay, then let's to be okay. That's the last lecture, so let's take a break. Think if I try to finish LSD, it'll take half an hour more. But let's try to be relaxed way today. Relax manner. And then take a rest. Okay, let's take a rest. So next I will plug this one into here and we will see what's going to happen. Let's take a 10 minutes break. 10 minutes break from now. And if you have questions, just tell me. And if should I bring the graded homework from my office? I think okay, I should bring actually. I will go to my office and come back. You guys can freely chat. Yeah, I'll be back in 10 minutes.
这个 probability 你们它就长成这个样子，它会有一些 probability 会有一些扣，会有扣，会有多个扣。但正常来说，你方式是会有，大多数情况你遇到标准的方式就是它不是就是它这个是不是有生产力，就是说你既然是画张。方式我发现跟方式其实应该会讲，就是它相当于提供就是有可能中间有个地方没来得及看到上一个数式形式，是一个某种例子，它中间这个 problem 可能是某种例子作为这个，它可能是方式的项目，就是说你方式的是你方式的是什么，而你这里面就是三。我真的说，就比如说你一个月拍照的时候，光是这个实际上它是它强的，你没办法分辨。这个这不上我在就是上你可以认为它是因为它对于不同的你们是哪一种？你的删了是哪里来说的？它这个我记得我们学过一句话，你拿的是拿的能的不是数量，能带对你激发的你普密度函数取的那个对，普密度函数只是你能的在这个东西在函数的而已 ，m 能的。这所以。所以你的不同难的这是不错的。 第八题，这是哪个？第一个，第二个，第三个，然后后面是一个。他们的后面是后的，的。第三，就是是这样，就是对，就这个，就所以这个是后的，说这个东西，咱们这些这个。不同，这个算，它算什么呢？就这可以可以说它肯定有出去，你可以说你某种它这个是在分批。这个东西，我觉得这个东西有点好，就是头脑的。这里是能不能？南茂林，南茂林，就是说，南茂林是代表某一个激发态的某一种激发状态，后来为就是对，就你有不同的激发，它这里就开了一个三种某一，这里是三种，它一对。建议比较大气，咱们可以如上一上可以拿到这还包税一上的为什么？就是你想让我当是这样，它是一个动量的合成，是还是跟动量有两个例子。注意，这里取的是南乐里，这里取南乐里，电能到这个500伏，南乐零，南乐零，如果你有两个，我取动量为还有你有两个，保证动量长的，我只要有两种汤，让它动量可以都会有自我变的，会自己反应。如果你接这个就是它不能，就容易产生，微变之类。所以，其实它跟能量不一样。然后，所能量和 M 说直接挂都是。
So the way I want to submit the homework by hand today. And if you submit the homework, so you can pick ready homework from here.
我觉得这个可能
Okay.
先你做上酒店，有吗？还有第一个是调这个调了这个方式，就这个都那个算那个上次的算一组我也有屁，这代表啥？哦，这个后面代表那个学屁股不是学生哪里？这里可以不是修正，你要是没修正的话，你要是你相对工作你可以不。
Question? Or do you want to submit by hand? Okay. So if you want to submit the homework by hand, just give it to me.
我觉得讲这个 zero， 这个是你哪会？对我理解它，为啥？为什么一定是两个？
Okay, as I promised. So now, okay. So I will play the Weinberg's speech, which is actually fantastic. I think some of you already may listen, but it's very nice one. So I just share the draft via WeChat, and it's a long one, so I just stop in the middle. ABC is enough. I think this is some motivation to the QFT2. Since you have learned of QFT1, like a difficult QFT1 by me, and QFT2 will be given by the Xiaoding Yu. I think I heard his lecture is more elaborate, a bit slower than more elaborate, but so that it's more understandable to people. But anyway, so yeah, so mine's a more difficult one. But anyway, so this QFT2 will be given the Xiaodong Yu, and this speech will be motivation for QFT2. Okay, let me play. Just a moment. Hopefully, you can listen. What happened? Sorry, there's something wrong. Why there is no audio? Oh my goodness, if I use 10 cent, does audio doesn't show up here? Strange thing. Just a moment. There is something wrong about the audio. What's happening? What's going on? Or maybe I need to switch off my voice. Oh, good. Okay. Okay. Maybe this one is better for audio, maybe. Okay. So the transcript in the widget. So hopefully. Okay. Good.
Physicists naturally try to see phenomena in simple terms. You might say that the primary justification for doing elementary particle physics, with all its expense and difficulty, is the opportunity it gives us of seeing all of nature in somewhat simpler terms. Great progress had been made a few years ago, say from the late 1960s to the mid 1970s, in clarifying the nature of the elementary particles and their interactions. Then, starting about the mid 1970s, we began to confront a series of problems of much greater difficulty. And I would have to say that very little progress has been made. I would like, first of all, today to remind you of what the present understanding of elementary particle physics is, as it was already formulated by the mid-1970s, and then for the larger part of my talk, discuss the attempts that have been made since the mid-1970s to go beyond this to the next level of simplicity. The present understanding of elementary particle physics, I would say, is based on three chief elements. First of all, there is a picture of the interactions of the elementary particles as being all extremely similar to the one interaction that was earlier well understood, the electromagnetic interaction. You know that the electromagnetic interaction is carried by a massless particle of spin 1, the photon, which, for example, is exchanged between the electron and the proton in the hydrogen atom. In the present understanding of elementary particle physics, there are 12 photons, and I should do this, meaning that the word is put in quotation marks. There are 12 photons which carry all the forces that we know of between the elementary particles. These 12 photons comprise, first of all, the familiar old photon, which is emitted, say, by an electron or by any charged particle, and then by three siblings, three family members, called intermediate vector bosons, a W minus, a W plus, and a Z0, which are emitted, for example, when leptons change their charge, when electrons turn into neutrinos or neutrinos turn into electrons. And the neutral one, the Z0, is emitted by electrons and neutrinos when they don't change their charge. Similarly, the W and the Z are also emitted by quarks when they do or do not change their charge, respectively. Physicists naturally, in addition to the four, quote, photons, unquote, of the electroweak interactions, there are 8 similar particles known as gluons that Sam Ting has already mentioned, which are emitted when quarks change not their charge, but a different property which has been humorously named their color, so that a green quark may turn into a red quark emitting a red-green gluon. There are 3 colors, and hence there are 8 gluons. You may ask, why not 9 gluons? And I will tell you if you ask me privately later. Now, in electromagnetism, we have not only the general idea of a photon, but a very clear picture of a symmetry principle of nature, which determines the properties of the photon and determines, in particular, all of its interactions, the principle known as gauge invariance. In a sense, from the point of view of the theoretical physicist, the photon is the way it is because gauge invariance requires it to be that way. The 12 photons of the elementary particle interactions as we know them are also governed by a principle of gauge invariance, but the group of gauge transformations is larger, and it is known mathematically as SU3 cross SU2 cross U1. The SU2 cross U1 is a 4-dimensional group which governs the 4 particles of the electroweak interactions. The W and the Z transmit the weak nuclear force, which gives rise to radioactive beta decay. So this whole set of interactions are called the electroweak interactions. And the SU3 governs the 8 gluons, which give rise to the strong nuclear forces. This is sometimes called the 3-2-1 theory. The theory of the 8 gluons by itself is what is known as quantum chromodynamics. The electric charge of the electrons, say, is in fact just a peculiar weighted average of coupling constants, G and G prime, associated with these 2 groups, SU2 and U1. G and G prime play the same role for these groups of gauge transformations that the electric charge played in the older theory of quantum electrodynamics, and the electric charge, in fact, is given by a simple formula in terms of them. And similarly, there is another coupling constant. A coupling constant is just a number that tells you the strength with which these particles are emitted and absorbed. There's another coupling constant that tells us how strongly gluons are emitted, say, when quarks change their color, known as G sub S for the group SU3. Now, this is a very pretty picture, especially since, based as it is on familiar old ideas of gauge invariance, it requires us really to learn very little new, which is always to be preferred. But there's an obvious difficulty with it. That is that gauge invariance requires that the vector particles, the spin 1 particles that transmit the force, have 0 mass. Just as, for example, electromagnetic gauge invariance requires the photon to have 0 mass. But of course, the W and the Z do not have 0 mass. They have masses which are so large that no one so far has been able to produce them, although we have strong reasons to think we know where they are. The explanation for this is now universally believed to be that the gauge symmetry, although precise and exact, in no sense approximate, is subject to a phenomenon known as spontaneous symmetry breaking. That is, these are symmetries of the underlying equations, but they are not realized in the physical phenomena. This is a lesson that elementary particle physicists learned from solid state physicists who understood it much earlier than we did, that symmetries can be present at the deepest level and yet not apparent in the phenomena. The symmetries are just as fundamental as if they were not broken, but they're much harder to see. Because the electroweak symmetry of SU2 cross U1 is spontaneously broken, the W and the Z have masses. The W mass is greater than 40 GeV, the Z mass is greater than 80 GeV, and the precise values are determined by an angle, which is just basically tells you the ratio of these two coupling constant. The angle is measured in a great variety of experiments, and on the basis of that, we believe the W will be a mass of about 80 GeV, and Z will be at a mass of about 90 GeV. Of course, we anxiously await confirmation of that. The second of the three ingredients, or the three elements on which our present understanding is based, is the menu of elementary particles. I won't dwell on this. There are 6 different varieties of quarks, of which 5 have been discovered, and the 6th is anxiously awaited. Each one of these varieties, sometimes called flavors of quarks, according to quantum thermodynamics, comes in 3 colors, so that altogether there are 18 quarks. And then in parallel to the quarks, there are doublets of leptons, neutrino electron, and then the muon, behaving like a heavier electron, has its own associated neutrino, and the tau lepton has its associated neutrino. Physical processes are most simply seen in terms of these quarks and leptons. So for example, when a neutron decays, a state which was originally an up quark and 2 down quarks of 3 different colors turns into 2 up quarks and a down quark of 3 different colors, a W minus being emitted, which then turns into an electron and an antineutrino. This menu of elementary particles is in no sense forced on us by theory, except for the structure of doublets of quarks and leptons and color triplets of quarks. The fact that there are 6 flavors is just taken from experiment, and it has to be regarded as just an independent empirical foundation of our present understanding. The third of the foundations of the present understanding of physics is more mathematical, but I think equally important: the idea of renormalizability. Renormalizability is very simply the requirement that the physical laws must have the property that whenever you calculate a physically relevant quantity, you don't get nonsense. You don't get a divergent integral, you get an integral which converges, and that is a finite number. I think we'll all agree that that's a desirable quality of a physical theory. The physical theories that satisfy that requirement are actually very easy to distinguish. If an interaction of some sort has a coupling constant G, like the coupling constants G and G prime and GS that I discussed earlier, and if that coupling constant has the dimensions of mass to some power minus D, let's say a negative power, D is positive. And when I talk about dimensions, I will always be adopting the physicist system of units in which Planck's constant and the speed of light are 1. Then, because the coupling constant has the dimensions of a negative power of mass, the more powers of coupling constant you have in the matrix element for any physical process, the more powers of momentum, which have the dimensions of a positive power of mass, mass to the first power, the more powers of momentum you will have to have in the integrals. So that as you go to higher and higher order in the coupling constant, you get more and more powers of momentum in the integrals, and the integrals will therefore diverge worse and worse. That's a bad thing. That's not a renormalizable theory. The allowed interactions, the renormalizable theories, are those with coupling constants, therefore, which are not negative powers of mass, but which are either dimensionless, like the electric charge of the electron, or a positive power of mass, like, for example, any mass. A physically satisfactory theory ought to be one which contains only such coupling constants. Now, that is enormously predictive, because the energy densities, or the Lagrangians, that determine physical laws always have a fixed dimensionality, mass to the 4th power. And I remind you that I'm using units in which Planck's constant and the speed of light are 1, so energy has the unit of mass and length has the unit of inverse mass. So therefore, if a coupling constant appears in an energy density and it multiplies an operator, a function f, with the dimensionality mass to some power d, then the dimensionality of the coupling constant must be just the dimensionality of the Lagrangian 4 minus d. So therefore, in order to keep the dimensionality of the coupling constant positive or 0, we must have the dimensionality of the operators 4 or less. But almost everything has positive dimensionality. Fields have dimensionality 1 for boson fields or 3/2 for spinor fields. Derivatives, space-time derivatives, have dimensionality 1. And therefore, as you make an interaction more and more complicated, its dimensionality inevitably increases. But the allowed interactions have dimensionality only 4 or less. And therefore, the principle of renormalizability limits the complexity of interactions that are allowed in physics. This is just what physicists need. They need something to tell them, do not think about all conceivable theories, think about a limited set of simple theories. The limited set of simple theories that we allow ourselves to think about are those with interactions whose dimensionalities are 4 or less, and therefore are sharply limited in the number of fields and derivatives that they can have. In fact, so powerful are these limitations that principles A, B, and C determine a physical theory uniquely, except for a few free parameters. The free parameters are things like the electric charge of the electron, the Fermi coupling constant of beta decay, the mixing angle between the Z and the photon, a scale parameter of quantum chromodynamics, which tells us where the strong coupling constant begins to become very large, and of course all the quark and lepton masses and masses for other particles called Higgs bosons that I haven't mentioned. But aside from this fairly limited set of free parameters, not as limited as we would like, but still not enormous number of free parameters, the physical theory of elementary particles in their observed interactions is completely determined. And not only determined, but agrees, as far as we know, with experiment. One of the features of this understanding, which I think is perhaps not as widely emphasized as I would like, to me it seems one of the most satisfactory aspects of what we know about physics, is that the conservation laws of physics that were painfully deduced from experiment in the 1930s, 1940s, and 1950s.
I think it's about the end of the. There's some problem in the Tencent side. I'm sorry if it is the case. Let's see. Stop sharing. How can I stop sharing? Okay, I think there's some problem in the Tencent side. So if it is this problem, I'm sorry. What's happening now? Let's see. Okay, I think we finished the ABC. I think this. I wish I could be like as clear as Weinberg. Unfortunately, I cannot reach his level. This speech was wonderful. If you want to continue, you can watch this. The link I will send you your WeChat. I think I already sent, right? I already follow. But anyway. So this is the case, and I will continue my lecture. But unfortunately, Tencent side, I cannot. What's going on there? Why Blackboard doesn't show up? I'm very sorry. What's going to happen?